All right. Good morning, everyone. In this course so far, we've talked about a lot of different things, but for the last few days, we've been focusing on a topic in particular, and that's tension members. So far, we've covered pretty much all of these first three equations here. We have the ability of a brace to yield excessively in tension. We want to prevent that, to prevent collapse, full or partial of the structure. We've got the potential for the tension member to fracture at the net section at the connection. And so we've got two ways we can have fracture happening. One is the net section fracture, where we just go straight across a tension plane that accounts for the loss of bolt holes or the loss of some steel being affected in tension through the fact that we only have some of the elements connected sometimes. And then the other day we talked about this bigger, longer equation, which was another way that you can fracture a connection, except in this case, we don't have pure tension, but we have some tension and we have some shear. Okay. So in terms of covering these three equations and what they mean for the failure of tension members at the ultimate limit states, we've covered all of that material today. To date. What we haven't talked about yet is what actually happens with the bolts that are connecting the tension members to the gusset plate. And so what we're going to focus on today is discussing the limit states associated with the actual bolts that are connecting the tension member to the gusset plate. Sometimes bolts carry loads through shear, and sometimes bolts carry loads through tension, as you might be able to guess so far. For the most part, we're going to focus on bolts that carry shear. Once bolts start to carry tension, things start to get a little bit more complicated, not because of the way the bolts fail, but because of the way that the tension member essentially, usually the way you have to, I'll show you a slide in a minute and might make things a little bit clearer, but I'm going to focus on bolts carrying shear for the most part in this course. I'm going to look at a few new limit states then, basically today. One of them has to deal with the actual failure of the material around the bolt. Some of them have to do with failure of the bolt themselves. So we're going to look at the failure of bolts in shear and the failure of bolts in tension. And then I think we'll probably get to serviceability limit states for tension members next day. I haven't 100% committed to that yet, but I think that's probably something that I'll talk about. This last expression here, the slip capacity of a bolted tension member, I think we'll perhaps talk about next day, maybe. I haven't decided yet. Okay. What are bolts? Well, I'm sure everyone's seen a bolt before. I kept this slide from when I was teaching this course for the first time online during the pandemic, and I never really decided to make it any cleaner than this, but for the most part, a bolt is, well, you got the bolt, but there are a bunch of different things on the bolt. You've got the nut that wraps around the threads that helps tighten the bolt and to fasten it in place. We've got a washer that helps you to torque bolt. And then the bolt itself has a few different components. The bolt has the threads, which you spin the nut onto. The bolt has the shank, which is where the area is not reduced to account for the fact that we've got threads. Then we've got the head of the structural bolt. One of the things that makes structural bolts different from other mechanical bolts is that the hex head is quite a bit heavier. It's usually about 1/8 of an inch to 1/4 of an inch bigger than a typical mechanical bolt for the same diameter of the actual bolt itself. I'll pass this one around so that you can see what it looks like. This one is a 1-inch diameter. If you haven't been able to tell what 1 inch before is, usually if you put your thumb down, your thumb on average is about 1 inch wide. So if you use your thumb, you can kind of see, well, the bolt's about as wide as your thumb is. So that's about a 1-inch bolt. There are some variants of different structural bolts. This one, you'll notice that the primary difference between the bolt that just passed around there and this one is that there's no shank on this bolt. It's threaded all the way through the entire length of the bolt. That's because if you have different plate thicknesses, you might want to be able to tighten it up really small and have the ability to accommodate the additional plate thickness without having to worry about how long the shank is. And sometimes you might actually want to spin the bolt into a hole that's threaded. And so when you want to put threads into a hole, it's called tapping. And so you might want to actually spin the bolt into a hole in steel that has threads in it. And so in that case, you might use a threaded bolt. So those are both 1-inch diameter. From time to time, though, you might use a bolt that's a little bit shorter. I think those are about 4 inches long. This one's about 2.5 or 3 inches long. And for the most part, both the threads and the shank are a little bit smaller. One of the things you're going to see on the hex head, though, when you have it in your hand, when you're taking a look at it, there's going to be something stamped on the top. And the thing that's stamped on the top here is the grade of the bolt. So on the picture here I have on the slide, we have this A325 that's marked around the head of the bolt. That denotes the grade of the bolt, both in terms of manufacturing tolerances and in terms of the material requirements for that bolt. The last one I'm going to pass around here is a little bit interesting. It does not have a hex head. In fact, it doesn't have much hex at all. This is called a tension control bolt, and basically what happens is you don't do anything with the head at all. You put it in place, and then you have a torque gun at the back that's used to grab onto this little piece of steel here at the back. The gun holds into that and spins the bolt. And once the bolt is adequately tensioned and there's an acceptable amount of torque on the nut, they're going to shear that little piece off, and that's going to control the amount of torque that gets applied to that particular bolt. We'll pass another one here around in a minute, but we'll wait a little bit later to get into what's different with that bolt. Basically, after today, you should be able to determine if the bolts are carrying the force through shear or through tension. And for bolts directly in shear, identify the number of shear planes. And so single, double shear should come into mind, and I have a polar wear activity to help us think of that before we get into things today. Should be able to calculate the shear and bearing resistance of one bolts in shear. We're going to focus on bolts in shear. I'll show you how to calculate the capacity of one bolt in tension, but we're not going to focus on that in this course. And then finally, there are some detailing requirements about how closely spaced bolts can be, how they have to be proportioned within the confines of the member that the bolts are connecting to a gusset plate. And so there are some spacing requirements detailed in the steel standard that we have to be able to follow as well. Does anyone have any questions about why these three things might be important before we get into the technical material for the morning? So my little window here, for some reason, I don't know why this one never works, so I'll put this over here. Oops. That's one thing about making the screen extra wide, I guess. Let's see if I can present this. So I guess I'll change the projector here for a moment. So just a reminder, because we do need to talk about bolts and single and double shear, and it's important that you remember what this means, not just because I told you what it is, but because you learned this in previous courses. We've got bolts and double shear, and what's important about bolts that might be in double shear? A, they share the stress over two bolt areas. B, they can carry twice the load as bolts in single shear. C, wait, aren't those the same thing? And D, I'm not sure. I forget everything that was ever taught to me in 2023, and Taylor's going to have to tell me again what bolts and double shear are. So it looks like we've equated to about the 10 answers that we're going to get here this morning anyway. The right answer here is C. Wait, aren't those two the same thing? Sharing stress over two bolt areas, right? Basically, a bolt and double shear carries the shear not just through one diameter of the bolt, but through the other diameter as well. If there are two shear planes, then the stress gets shared over two areas. The result of the stress being shared over two areas is that bolts and double shear can carry twice the load of single shear. Okay, so that was kind of put there on purpose, hoping that people would recall what bolts in single or double shear were. We'll see what that means today, and we'll see what the implications of that are for us in terms of how we're going to approach calculating the strength of our bolts in double shear. So the way that bolts transfer force is primarily through shear when they're arranged this way. And generally the reason for that is, well, we've got two members that are lapped together. Perhaps one side is the gusset plate, maybe the other side is a flat bar. It doesn't really matter what they are. But through those members that are carrying force longitudinally through them, we poke some holes and throw some bolts in those holes so that, pardon me, such that the bolts are transverse or perpendicular to the applied load. And so basically what that means is that we've got, in this case, one single transfer line between one side of the tension member and the other tension member. And that's what we're going to be calling in this course a shear plane. Okay, so basically the shear plane in this case is intercepting the bolt roughly, well, just at the start of the threads in this case. So just outside of the shank area, just into the threaded area. And so we're generally going to be transferring that force through shear across that bolt on that single plane. How this tends to work is that there's a bearing stress that develops. Oops, I guess I should go back here. Do I not have? Yeah, there we go. And so, yes, I got ahead of the horse a little bit here. So when you first install the bolts, the tension members tend to, well, they're not in complete contact, but as we apply tension force, those tension members start to slip relative to the bolts. We develop some bearing on the bolt up here, so there's some bearing stress that develops on the left-hand side, some bearing stress that develops on the right-hand side, and it's ultimately the equilibrium that develops through that plane. This might be, for example, the tension force divided by the number of bolts in the connection. This would also be the tension force, oops, sorry, I should have it the other way. The applied tension force divided by the number of bolts acting on this particular bolt as well. And if we were to try and draw a body diagram, well, shear in that bolt is basically going to be proportional to the bearing force acting on the bolt between the bolt and the plate. And so basically there's this shear force that we're designing each of these individual bolts for, which is the factor tension force divided by the total number of bolts that we have in our connection. If we start to fail the bolt in shear, you may or may not have seen shear failure before, but it is literally like a dislocation along the vertical plane here. You can see in this case the bolt is deformed one side relative to the other, maybe by about a millimeter or 2 millimeters. It is a pure shear stress, pure shearing of that bolt. And when bolts are in single shear, there's a single face here that's going to be used to reduce or to carry that shear force through the tension member. Okay, so basically what's going on here is the tension member transfers the tension in the two components in the bolts through bearing. That results in a shear stress through one of the diameters of the bolt when we have bolts in single shear, and that can cause the bolt to start to fail on this identified shear plane. And it basically depends on the strength of the bolt and the area of the bolt, generally speaking. Are there any questions about what the load transfer mechanism looks like for bolts to tension members, what it means to have one tension member bearing on the bolt, what the implications might be for the design of the tension member itself later on? Any questions in general about anything that we've talked about so far? Or any questions about the bolts that I passed on? Anyone have any interesting observations about anything? It's Monday, I get it. We also have to look at the potential for bolt and double shear. And generally what happens is as soon as we add another plate, perhaps to this connection, so this might be that little tension member that I showed you earlier on when we first started talking about tension members. Maybe there's two thin plates on one side and a thicker plate on the other side. Now we're transferring that force through bearing on two parts of the bolt on one side and one part on the other. And that's going to activate this bolt through two separate shear planes. Right now we're transferring that stress not just through a single diameter, but now through a different diameter. So here we have basically TF over the number of bolts. And up here we have TF over the number of bolts divided by the number of shear planes. We're going to call the number of shear planes M. Okay, so TF over the number of bolts over the number of shear planes. So basically, we've got on one side of the connection TF, and we've got TF over 2, basically in this case, or over the number of shear planes. And so when we start to intercept the bolt at more than one location, we start to add shear planes, and that means that the stress is getting shared now between two cross sections of the bolt instead of just the single bolt. So every time we add a new plate in that arrangement, we add a new shear plane. And how that starts to look is if we're trying to fail a bolt in double shear, we're also intercepting those two faces. And so we can see here in this image that we've got basically, well, double shear. We've got one plane here failing in pure shear stress, another one here failing in pure shear stress. And the sum of those two shear stresses times the areas is going to be giving us the strength at the bolt at failure. So I'm going to be passing around another bolt here. This one is 3/4 of an inch, I believe, A325. I'll tell you what that means in a minute. But this one was part of a test where the bolts failed in double shear. And so you're going to see that ultimately it looks very similar to what we've got on the page here. Usually only one face is actually going to fracture when we reach the strength of the bolt, but both the faces there are working quite hard, and both of them deform significantly before the bolt actually fails in shear. Okay, does anyone have any questions about what's new here, what's different between bolts and double shear, perhaps even bolt and triple or quadruple shear, anything about how that bolt is going to be sharing that stress differently, or how we might get more strength out of a bolt that's connected in double shear? Double shear is just a fancy word to say that the stress is divided into two areas. Generally speaking, it's not super practical to have bolts in double shear. There are some examples. And so if you, for example, have a gusset plate in plane and you connect a pair of double angles or something like that to the gusset plate using bolts, those bolts are going to be in double shear. But that's pretty much the only practical situation. For the most part, we're going to be having bolts in double shear. For the most part, it's generally speaking from an constructability standpoint, more likely that we're going to be connecting things together so that we have bolts in single shear. In addition to the fact that bolts can fail in shear planes, we can also develop failure in the tension member itself. And so as I mentioned before, the bolts are taking this, are transferring this tension into a shear force, but ultimately there's a bearing stress that's developing between the bolt and the plate itself. And what that bearing stress can do is start to squash out the steel. You can see here there's some yield lines kind of out this way, and you can kind of see from the flaking of the material off the plate around the hole, that stress sort of propagates outward, similar to if you had like a foundation on soil. The stress kind of goes out towards the area in front of the bolt, and as that material fails, the bolt moves significantly from the original location, which is in the center of the bolt hole, something like this. It moves out through the steel, and this is what we call bolt bearing failure. There's a failure of the actual steel material in the tension member itself that comes from the fact that the stress of the contact between the plates and the bolt is too much, and that starts to push the steel out without developing this block shear tear out mechanism that we talked about before. We're not getting any tear out here of the bolts, right? We're not getting that. It's just pure failure of the material around the bolt hole and bearing between the bolt and the tension member itself. Are there any questions about what this bolt bearing failure means, or what the implication might be for us when we're thinking about how bolts transfer the stress from the tension member in the bolts through shear and ultimately into the gusset plate we're trying to take the force to? Awesome. So, for example, if we want to look at this picture, let's just say we've got a force here in the brace or whatever that's getting connected. Maybe we have a shear force in the beam. Maybe we have a shear force or an axial force in the beam here coming out this way. Can anyone tell me how these bolts might be taking any of these forces? Is it going to be bolts ultimately transferring that force through shear, or are those bolts all going to be transferring forces through tension? What do you think? Maybe let's focus on this one first. We've got a tension member that's bolted to a gusset plate. There's nothing on the other side. Are those bolts taking the force through tension or through shear in the bolts? Shear, right? The bolts are perpendicular to the applied load. That means we're going to have a shear force in them. There's no plate on the other side, and so are those bolts in single or double shear? Single shear. So there's only one shear plane that can develop here. We've got the gusset plate, we've got the tension member, we've got some bolts through it. There's only the one shear plane through which we can transfer that force from tension in the member to shear in the bolts. And similarly, on the other sides here, it's pretty much the same deal. Despite the fact that we might have perhaps two components of force here, we would still be transferring that force ultimately perpendicularly to the bolts, and so those bolts would be in shear and in single shear. So what does that mean for us practically speaking? How do we quantify what the strength of the bolt will be in shear, and how do we determine how strong the tension member is resisting this bearing failure where the bolts just sort of plow through the steel from the original position in the original bolt hole to something further down. In clause 13.12.1.2 of the CSA S16 standard, it gives us some expression that we can use to calculate the strength of these bolts in bearing and in shear. If we're looking at bearing, basically this is the failure of the steel material. All right, so if we've got a certain number of bolts bearing on the holes, this is a single bolt hole, for example, with a single bearing area. We've got a thickness of that plate, and the stress is going to develop over the width of a single bolt. So what we're going to see here in this expression is the number of bolts, which makes sense if we've got more bolts in bearing. There's a reduced bearing stress at each of the contact areas. It's proportional to the thickness of the plate, which makes sense because that's the thickness of the plate that's actually carrying that bearing stress. We've got the diameter of the bolt, which I guess you could say makes sense because the contact area, if you make it over the width of the bolt, is basically proportional to the diameter of the bolt times the thickness, right? That's the area carrying bearing, and it's proportional to the ultimate strength of the structural steel that we're connecting. Okay, so this all sort of makes sense from stress times area kind of perspective. The more bolts, the more bearing areas we have, thicker the plate, the bigger the bearing area, the bigger the bolt, the bigger the bearing area, and ultimately the stronger we'll have that to be in bearing. We've got a different resistance factor here that's 0.8, and that's just to target a different reliability index here. This is more of a kind of rare situation. Usually with bolts and bolt connections, we use a slightly higher reliability index when we're designing these. The thing that usually sticks out to people is this 3 out here, and that 3 seems a little bit weird because why are we multiplying all of a sudden the force from one contact area by a factor of 3? And that's basically to account for the fact that the bearing failure happened through a significant amount of yielding in this area that's downstream, so to speak, from the bolt hole itself. And so it's able to mobilize that bolt, all this area around it has to fail. And so the idea is if you spread out the stresses from contact area to the area that's actually filling and bearing, it fans out, similar to what you might have in a foundation on soil. The stresses fan out this way. And generally, they say, well, it's proportional to about 3 times the bearing area, okay, because we got a significant amount of stress fanning out from that bolt hole. That helps to increase the resistance bearing, and so we have a factor of 3 on that expression. It's very important here to note the fact that this is the ultimate strength of the connected steel, because we're going to see in a minute an expression for strength of the bolts that are based on another FU, and the FU is the strength of the bolts. And every single year I say at the front of this class, don't forget that when you're doing bearing, it's the strength of the actual tension member. When you're doing bolts of shear, it's the strength of the bolts themselves. And every single year, someone on the exam used the wrong ultimate strength in the equations here. This one is almost always 450 MPa if we're using 350W steel. Okay, connected steel. Always remember that that's the case. Do not use anything other than FU for the steel, which is usually 450 MPa for these calculations. Does anyone have any questions about what goes into this equation or what it is that we're actually calculating when we use an expression like this? Okay. Next is the bolt shear. We can fail the steel in the tension member, or we can fail the actual bolt. And so in this case here, things here start to make a little bit of sense if we start to look at what's going on in this equation. Well, we've got the number of bolts. Of course, we've got 2 bolts. Those are going to be stronger together than 1 bolt. The number of shear planes, if we double the shear planes, the strength is going to go up, and so that makes sense. The cross-sectional area of the bolt, the shank, right, if we're interested in the shank of the bolt where the area is not reduced to account for the threads, that's the full cross-sectional area of the bolt. And this is important. FU in this equation is the specified tensile strength of the bolts. And the only reason I say this is important is because the ultimate strength of bolt material is significantly different from the ultimate strength of the steel that we're using in the rolled sections that we are using for the primary structural members. Okay, when we're looking at bolts, the strengths can often double compared to what it is regular steel. And so this is usually something on the order of 825 megapascals, and I'll share some other information on that in a moment. but it's important that you get the context for how using these two numbers incorrectly could result in very different resistance calculations when you're actually applying them in these equations. So this part makes sense. Number of bolts, number of shear planes, 2 bolts times 4 shear, 2 shear planes. If we have 2 bolts and double shear, it's 4 times stronger than 1 bolt and single shear. Well, remember, because we're using tensile strength properties, when we're talking about the strength of things in shear, we multiply by 0.6 to account for the fact that the failure stress for elements in shear or steel in shear tends to be about 60% of the failure strength in tension. Okay, so basically we're saying 0.6 on the FU, that's the strength in shear multiplied by the area of the bolt multiplied by the number of bolts multiplied by the number of shear planes. It's a pretty straightforward expression to calculate the resistance of bolts in a tension number that's transferring the force to the bolts in shear. Does anyone have any questions about what the expression is doing or how we might use this, for example, to calculate the resistance of a bolted joint, for example? Okay. So as I said previously, for the most part, the most common assemblies bolts are grade A325 and grade A490. We've got a specification. This is an ASTM specification, F3125. And basically that specification says there are a couple different grades. A325 has to have a strength of 825 megapascals. So roughly, almost, anyway, twice the strength of your typical 350W steel in tension. And then we have A490, which tends to be a little bit stronger even than that. We get up to 1,035 megapascals. We're looking at the strength of A490 bolts, more than twice the strength of typical rolled steel in tension. Okay, so remembering when to use these values in this expression and not in this expression is important because you'll get vastly different values if you use the wrong ultimate strength in those calculations. A307 don't really use very much. And then down here, I've got the metric equivalents. So these are all the imperial standards, A325, A490. There are metric equivalents, A325M and A490M, that they exist, I guess, in theory. There's a reason here, though. That bolding on the top 2 lines, that's not my bolding, that's the bolding in the handbook. Any ideas based on what we've perhaps said before, why those values for imperial designations might be bolded, where the ones for metric designations might not be bolded? When do you want to bold text in any context? You want to bold stuff if you want to stand out, right? Why do we want the imperial standards to stand out to engineers using the handbook compared to the metric standards? We use metric, don't we, in this country? For the most part, despite the fact that we are a metric country, we still don't work a lot in terms of engineering and construction using metric units. And so just in terms of whether or not you're actually going to be able to find a metric bolt. And so, for example, these imperial bolts, they're 5/8, 3/4 inch thick. These ones might be 20 millimeters, 22 millimeters, 24, 26 millimeters in diameter. You will not find those in the marketplace. If you specify metric bolts, someone's going to give you a call and say, look, you must have just graduated. We don't use metric bolts anywhere. We only use imperial bolts. And so, can you please specify an imperial bolt so we can use that on a project? If specify 26 millimeter diameter bolts, A325M, you're going to delay the project probably by 6 months because nobody makes them. All right, so just remember that despite the fact that we live in a metric country, we're using all these metric dimensions and units to do our calculations. You're not going to be using metric bolts on any of your projects. The one last thing that's important to say here is that when we have a shear plane, we generally want to intercept the bolts with that shear plane through the shank. Because when we intercept bolts through the shank, that's where the area is going to be the biggest, right? So I'll grab these 2 bolts here. So if we look, and I'm sure everyone got to see, but the threads, right, they're smaller, and that's what's the note here. The threads generally have to remove area to make the threads compared to the area of the shank. That means that there's more area in the shank than there will be in the threads. So that means the shank is going to be stronger, right? More area to carry the same strength versus smaller area to carry a reduced strength. When you intercept the bolt through the shank, then you can use the expression that I showed you previously, the 0.6 EBNMA ABFU. But if for some reason the plate steel is sufficiently thick so that you start to transfer that stress through the threads, all of a sudden you're reducing the area, right? And so there's higher stress on that area than if you're transferring the same force through the shank. And so in this case, we multiplied the resistance calculated using that equation using a multiplier of 0.7. That's basically saying, well, the area through the threads is about 30% smaller than the area through the shank. Okay, so we get an area reduction if we're intercepting the threads, and we account for that by reducing the strength by 30%. Now, like I said about whether you're drilling or punching holes, the bolts are usually designed and specified by necessarily, but the arrangement of the bolts is going to be specified and designed by the connection designer and the fabricator. Generally speaking, you know what kinds of bolts you have in your shop. And so you'll know if you've got a shank that's like 2 inches wide versus 1 inch wide, and you can make sure as the connection designer that you're not going to be intercepting threads. But from time to time, you just have a weird connection, and ultimately you just have to intercept the threads, and in that case, you can use reduction here. Generally, you want to do this as often as possible and avoid this where possible, but it's not always going to be avoidable. So with that in mind, let's just say that we've got a bolt that's in double shear, such that one of the shear planes is through the shank, and the other shear plane is intercepting threads. What are we supposed to do in this situation? Are we supposed to, well, think about it. Think about it for 30 seconds or a minute. Think with the next person next to you. I just want you to talk about what you might do with the stuff that we've already talked about so far. If we've got a bolt that has the shank intercepted by one of the planes and the threads intercepted by the other plane, if the bolt's in double shear, how are we supposed to handle that situation when we're doing our bolt strength calculations? Take a minute or so to talk with the person next to you. Just think about it, discuss it, and I'll come back and see if anybody's brave enough to share their thoughts with us. All right, I think that's good enough. Whether or not you talk about this or you talk about something else is probably a good to just have a quick break from listening to me drone on all morning. For those of you who took a minute to discuss what we might actually do in this situation, does anybody have any ideas that they feel comfortable sharing with the class? I need to start like bringing candy or something. I'll have lots of candy after Halloween. I can start bringing to class. Well, in this case, there are a bunch of different options, right? We could say, well, you know, the bolt's weaker through the shank, or sorry, through the threads, stronger through the shank. The first thought that comes to mind might be, well, you know, in this case, we're feeling the bolt through the shank and feeling the bolt through the threads, so we'll take the strength of the bolt through the shank and the strength of the bolt through the threads, add that together, and call that the strength bolt. Did anybody think of that or suggest that in their discussions? The other thing that you could do is say, okay, well, it's weaker through the threads, and so let's just calculate the strength of the bolt through the threads and multiply that by 2. That's conservative. Did anybody think of that in your discussions this morning? So there's take the strength of the bolt through the threads and multiply by 2 because that's conservative. There's also take the strength through the threads and multiply by 2 because that's just from static equilibrium what the situation is going to be. So the reason I say that is because the force up here, right? Let's just, I'm drawing that the wrong way. Let's just call this whatever the factored force is divided by N. And this is the factored force on tension member divided by N divided by M, right? And this is factored tension force divided by the number of bolts divided by the number of shear planes. And so in this case here, we've got a force on one side and a force, I got the total tension force coming through the connection, TF over N, and a resultant tension, basically, if we think of this in terms of the supports, reactions. If we just turn it 90 degrees, we can think of this as if it's, you know, a point load in the middle, and we've got a couple reactions out here. Well, if we're going to apply a load to this beam, and the strength of the support over here is, let's just say 70% of whatever the strength is, let's just say VR, and this one is VR. We've got a resistance of one side and the resistance of the other side. It doesn't really matter when this case is going to fail versus this one. It just means that as soon as we get to a total load of 1.4 VR on the beam, we're going to fail the support here, right? Because from equilibrium, the total force here, these two have to be equal. And so the strength is VR, but as soon as we apply 1.4 VR, we're going to fail this one at 0.7. And so just because the strength is bigger up here doesn't mean it's actually going to see that strength. We're basically going to, fracture the bolt through the threads at a force that corresponds to the actual reduced force or the reduced strength on the threads. We're not actually going to fail the bolt through the shank. And ultimately, if as soon as one of these two shear planes fails through the bolt, we're going to fail the connection. Right? If we start to shear off all the threads, it doesn't matter how many shanks we've got, we've reduced the connection strength significantly. And so in this situation, we want to calculate the entire thing depending on the number of shear planes. And it doesn't matter if we're going through the shank and the threads in two different locations. We're always just going to take the 0.7 multiplier and multiply the strength by that 0.7, regardless of whether or not one of the shear planes is intercepting the thread or not. Okay, basically the bolt's going to fail as soon as the stress on one of the threaded areas reaches its failure strength. It doesn't matter if the shank fails or not, that's when the bolt's going to let go. Okay, does anyone have any questions about how we'd handle the situation before we continue on with the rest of the lecture this morning? Okay. So there are some times when bolts might carry tension. For example, I showed this in the introduction to tension members. There might be a hanger that's carrying some kind of, maybe I'll use a lighter, uglier color. It shows up so much. Oh, that's not bad actually. We've got a tension force from the hanger. And in this case here, I'll zoom in a little bit. We've got these 4 bolts up here. And those are going to be carrying that tension force directly through tension in those bolts because, well, we're pulling down on the hex head. And we're actually transferring force longitudinal to the line of the bolts. So in that case, those bolts are actually going to be carrying the load and tension. Now, the problem that makes this difficult is because when we start to do stuff like this, and we have a hanger, I'll draw it like this, and a plate, and we've got a tension force acting down on it and bolts here. When the plate is really, really thin, the plate is going to want to bend. And we're going to get additional contact forces. We're going to start to apply a teeter-totter kind of effect, and we're actually going to be amplifying the tension on the bolts to a higher level than what you'd think would be present just for the applied force. Okay, we're not going to get into that in this course, but I do just want to give you some context for when bolts might be in tension, when to look for that, and if you want to see how to handle bolts in tension, considering this prying effect that I just waved my hands about for about 10 seconds. You can take C5063 with me next winter, next year. But if we do have bolts in tension, we're able to quantify the tension force on each of the bolts in the connection. It's basically going to be very similar to what we had for shear, except this is the strength of a single bolt, a bolt in a joint, and not all of the bolts in a joint. You'll see that the 0.6 is gone, but we maintain 0.75 in front of phi b a b f u. This should be pretty familiar, right? A tensile strength times an area times a resistance factor is the strength of something in tension. This 0.75 is just there to account for the fact that, well, it doesn't matter where the shear plane is. Whenever you're applying a force to a bolt in tension, it's basically going to get transferred through the head of the bolt into the washer and nut assembly. And so it doesn't matter where the shear plane is, the tension's always going to eventually pass through the threads, right? So there's a smaller area where the threads are reducing that area to basically turn it in tension, or they're going to increase the stresses on the section. And so despite the fact that for shear, that multiplier is 0.7, for tension, they found from tests that basically 0.75 provides a sufficient level of reliability. And so it's basically the same thing as multiplying the component by multiplier 0.7. So I don't really care if you have questions about that or not, because we're not going to talk about it again in the course. I just wanted you to see it and know that that is there for you if you need it in the future. The last thing I want to talk about before we get into a reasonably quick example is that we do have to make sure that our bolts are detailed in a certain way. And if we don't detail the bolts in this way, we can't do any of the stuff that we've talked about from lecture 11 onward. And so when we're detailing bolts, remember that value pitch, gauge and pitch, S and G. There's a minimum distance. You cannot space bolts closer together than 2.7 times the bolt diameter. And so what that means is you can't make tension connection where the bolts are like this, right? It's just silly. First of all, you can't get a wrench on that to work any of the bolts anyway. And so they need to be at least 2.7 bolt diameters, which is something like that. It'll let you get a wrench on the nut. Even that's pretty close. Minimum edge distance means how close it should be to the edge, parallel to the applied load. That's in the table. Maximum edge distance is also in the table. It should be 12 times the thickness of the connected part, or 150 millimeters. And then minimum end distance. That's the distance between the bolt and the end that's being pulled out. And that generally also comes from table 5, but it shouldn't be less than 1.5 bolt diameters. Basically, there's a table here that tells you pretty much everything that you need to know. Again, the imperial bolt sizes are bolded because those are the ones that we use. And in fact, 5/8, 3/4, and an inch are typical values. So for the most part, nobody shears anymore. For the most part, everything is either sawn or jet cut or plasma laser cut. And so for the most part, you can get away with all the stuff over here. But when you start to shear edges, the material starts to get damaged. And so we start to have more strict distances or larger distances for end and edge distances, generally speaking. Now, all of this stuff is whatever it is, but I do have some rules of thumb that I want to share with you, because just following those values aren't going to get you in the right ballpark all the time. Generally speaking, the pitch of the bolts is going to be something between 75 and 100 millimeters, and a common value is 80 millimeters. That's just what it is, practically speaking. Almost everybody bases their bolts at an 80 millimeter spacing, at least up to 100. The gauge tends to be very similar, either the pitch or whatever is going to satisfy the minimum or maximum edge distances. Edge distances tend to be, just generally speaking, about 35 or 40 millimeters, and that's just the way that it's done. I don't know how to tell you about that, but generally speaking, it works for pretty much all the bolt diameters. And so when people are trying to set up their shops to drill holes at certain distances, if they set something that works for all the bolt diameters, they're going to be able to make it work. And so pitches of 80 millimeter and edge distances of about 40 millimeters. One is twice the other, and if you set all of your equipment to always drill those kinds of distances, then you'll be in a position to have a well-detailed connection. Okay, I'll talk about that a little bit more later on when we start talking about the design of bolted connections, but these are some numbers that we're going to come back to just to make sure that things fit. And ideally, the thing is that bolts have to be able to accommodate a wrench, other kind of tools, so that the people putting this thing together can actually put things together without having stuff interfering and getting in the way. Does anyone have any questions about why we are perhaps setting some typical values on bolt spacings and end or edge distances before we get into the example that I want to go to today? So a quick example here just to demonstrate some of the stuff that we've talked about. It's the same example that we went through on day 1 of tension members. Back to the original staggered bolt arrangement, we want to determine whether or not the 8 5/8 inch bolts are strong enough to carry this 580 kilonewtons from the exit plate. We're going to be assuming that the bolts are ASTM F3125 grade A325 bolts. Okay, so are the bolts strong enough in shear and in bearing to do this kind of, to carry this kind of force from the tension member into the gusset? Does anyone have any questions about what it is the example is asking us to do before we get into the actual calculations? If I can find my damn mouse, there we go. So this is supposed to be a pretty straightforward calculation. Here we're going to assume the threads are not intercepted, and if I was a person detailing the connection, I might try as hard as I can to make sure that that's the case. So we can rely on the fact here that the bolts are not intercepted. And so the piece of information we need here, we need to know that these are 5/8 inch bolts. We need to know how many bolts we have. We need to know the grade of the bolts, and we need to know if the threads are intercepted or not. So we've got 5/8 inch bolts. We've got 8 of them. They're A325. They're not intercepted. The other thing we need to know is if they're in single or double shear. I've shown you a picture of a brace that looks like this before, and in fact, I showed you a very similar brace previously here. Did we decide that these bolts are in single shear or in double shear? Single shear. Great. So we know the bolts are in single shear. So we know that in terms of shear planes, we have M as 1. In terms of number of bolts, we've got 8. In terms of FU, it's not 450 MPa for the bolts. We're looking at the strength of the bolt material itself. For imperial A325 bolts, we're going to be using a tensile strength of 825 megapascals. Okay, the diameter of the bolts is 5/8 of an inch. And the threads are not intercepted, so we're not going to be applying that reduction factor. So if we want to know the strength of the bolts, we can come back to slide 17 here, and we see it's 0.6 pb NMAB times FU. So we can put that together, 0.6 pb NMAB FU. That's 0.6 times 0.8. N is the number of bolts, M is the number of shear planes, and all of a sudden we have to calculate the area of a circle in inches. That's hard, right? Does anyone remember how to calculate the area of a circle? Pi r squared, that's one way. Is there another way that might work with using diameters instead of radii? Pi d squared over 4. Great. So we're going to do pi d squared over 4 for that calculation. What do we do with inches? We're working in metric, right? We need millimeters, megapascals to get newtons, or 10 to the 3 kilonewtons. How do we turn this into a diameter that we can work with? We've got 5/8 times what to give us the equivalent in millimeters? 25.4 millimeters per inch, right? So we have 5/8 of an inch, or 5/8 of 25.4 millimeters over 4, multiplied by 825 MPa. Of course, this gives us a value in newtons, but I always just go through the liberty of dividing by 1,000, because that's relatively easy to do. If we do that calculation, we should end up with 627 kilonewtons. Okay. Does anyone have any questions about how we got that number or what that number means? Well, in that case, what does that number mean? Are we good or are we not good when it comes to the strength of the bolts in that joint? The shear strength of the bolts is 627. They have to transfer a total force of 580 kilonewtons. Is that okay or is that not okay? It's acceptable, right? In terms of the limit states design framework, it's very unlikely that we're going to fail that connection by shearing the bolts through the shear plane, where we're transferring force and tension through shear in the bolts to tension on the gut plate. Okay, there is the calculation for bearing. I don't want to go over time again today, and so I will leave that to you to try to do on your own, and it's also in the example notes that I'm going to, or that I've already posted, I guess, with the lecture today. Today we talked about bolts in shear and bearing. The most important thing is that you're able to determine whether bolts are carrying tension or shear, and you should be able to identify whether the bolts are in single or double shear. You should be able to calculate the shear and bearing resistance of one or more bolts in here, and describe and check some of the bolting spacing requirements. I've detailed that a little bit in the example notes as well for the example we just went through. Does anyone have any questions about any of these three things, anything else we talked about or the example before we lecture up for the morning? All right, well, we'll see everybody in lab this afternoon.